Welcome to EE252 Electronic Devices and Circuits. Today we are going to move on to a different section on multi-stage amplifiers. During the past several lectures we covered the BJT amplifier and the small signal model. Today we are going to move on to multi-stage amplifiers, which is an extension of the single stage amplifiers that we talked about. Now we talked about different configurations: common emitter amplifiers, common collect amplifiers, and common base amplifiers. They had different features. For example, their voltage gain and current gain, as well as input and output impedances. Now today we are going to look at cascading transistor amplifiers, that is, connecting them in series. So why do we need to do this? Okay, so this is called cascading transistor amplifiers. Why do we need to cascade amplifiers? Okay, cascading multi-stage transistor amplifiers. Right. So why do you have to do this? Why do you have to cascade amplifiers? Now you see, when we used single stage amplifiers, for example, during the previous example we worked out, there were certain parameters that we calculated: input impedance, output impedance, in voltage gain and current gain. Now when we have an application, sometimes the parameters that we talked about may not be ideal for our application. So for example, the voltage gain we want may be very high. Maybe instead of 20 or 30 or 50, maybe we want a voltage gain of 500. Or maybe we want an input impedance of very high value, maybe mega ohms, and very low output impedance to drive a low impedance source. So in cases like that, a single stage will not actually cater for all the requirements. For example, for an ideal voltage amplifier, input impedance is infinity, output impedance is 0, and you can have a desirable voltage gain. But in the closest it gets in terms of these requirements is the common emitter amplifier, and that is basically why we use it very often. But still, input impedance and output impedance requirements are not as we need. The input impedance could be in the range of 1 kilo ohms, or maybe a little bit less, or maybe less than 10 kilo ohms or something. Output impedance may be again in the range of 1 kilo ohms. So in the previous example it was limited by the collector resistor, right? Likewise, so therefore we may not be able to actually achieve all the required features in a single stage. In such situations, we may have to combine multiple stages of transistor amplifiers. For example, common collect amplifier, it has a very high input impedance and a very low output impedance, which are actually ideal for a voltage amplifier in terms of input and output impedances. But its amplification, voltage gain, is actually unity, or actually a little bit less than unity. So therefore it is not a good voltage amplifier. So therefore, in order to combine all these good features, high input impedance, low output impedance, and high gain, you need to at least have multiple stages. For example, if you have input and output stages made up of common collect amplifiers, you can have high input impedance and low output impedance. But to achieve the high gain, you can then have a voltage common emitter amplifier stage in the middle, right? Maybe one, maybe more. So this is what we are going to do in this section of the lecture. So let's have a look at these things, how to achieve such an amplifier. So all this is done, the input impedance output impedance matching, to minimize the impact of loading. Okay, so let's have a look at a general block diagram. So we may have a source, okay, with a certain voltage as well as a certain source resistance. Let's call this source resistance RS, and your input voltage may be Vs. Okay, these are something that you don't have any control over. And you may have a load. Okay, there may be a load which again is connected to this. You don't have too much control over this. This is my load. Now what matters is what is in between these two. So my amplifier should be, the total amplifier should be a block like this, which should have certain properties. Say for example, voltage gain, input impedance and output impedance. These may be some requirements, and these requirements may not be achievable using a single stage. So what we do is we basically put multiple stages. So let's have multiple stages here. Okay, so this is stage 1, stage 2 and stage up to n stages. There can be multiple stages, and input is connected to stage 1 and stage 1 is connected to stage 2, and likewise each stage is connected by multiple stages to each other stage. Okay, so this is my circuit. Now the first stage has an input here. That input, let's call input 1, and it has an output here. That's the output 1, and this output 1 will be the input of this stage 2. So therefore this is the input 2, and it has an output 2, and that will be the input to the next stage, and likewise, and this will be the input to stage n, and this will be the output of stage n, and this is actually equal to the output voltage Vout. Vout is that. Okay, so therefore you see each stage acts on the next stage, and each stage has its own input and output impedances. So this may have an input impedance R in 1 and an output impedance of R out 1. This R in 2, R out 2. Likewise, this will be R in N, R out N. So for the first stage, you may have a voltage gain of AV1. For the second stage, we may have AV2. Likewise, you may have AVN for the nth stage. So what happens is the input for the first stage is actually the source, whereas the load of the first stage is in fact the input impedance of the second stage. So this will be the load of the first stage, that is RL1. Similarly, the source resistance of the second stage will be for the second stage, the source resistance of the second stage will be equal to R out 1, and similarly the output impedance of the second stage will be the source impedance of the next stage, third stage, and likewise input impedance of the nth stage will be the load for the n minus 1th stage, and from the actual load will be the load of the nth stage, and the R out n will be the source resistance of the nth stage. So this is as if you have another, so this you can represent each of these using a model like this. Okay, so this is basically what you would be having. Likewise, you'll have this voltage will be AV1 times Vs, or V1. Let's put V1. This is V1, right? This will be V2. This will be Vn. So likewise, you can find this will be AV2 times V2, and likewise, you can find all the parameters we want using this. AVn times Vn. That will be my output of this source. So if I want to find my overall gain, for example, that is AV, this value. Okay, what is that? Expression for that, AV will be equal to some multiplication of several terms. Now, if my output impedances are very low, right? For example, if ideal sources are there, in other words, R in is equal to infinity, R out, all these, okay, I is equal to 0 for I equals 1 to n. If this is the case, AV would have been equal to AV1 times AV2 times AV up to AVn. However, because we have these input impedances and output impedances which are not really 0, these values may not actually be just that. Okay, so therefore we have to find what exactly are these things. AV, overall AV, you see the definition of AV, if you remember, is equal to the load voltage divided by source voltage. So therefore if you go by this equation, you see V2 is equal, so this will be equal to VL divided by Vn times Vn divided by Vn minus 1, going like that, times V2 divided by V1 times V1 divided by Vs. Okay, so it will go like that. So what are each of these terms? So V1, so let's start from the from the last term. What is V1 over Vs? V1 over Vs is the ratio, so this is V1, Vs is here, so therefore you see that V1 is the voltage or the potential division between Rs and R in 1. So therefore this is equal to R in 1 divided by R in 1 plus Rs. Okay, similarly V2 over V1, V2 is the output of the first stage, which is also the input to the second stage, right? So this is basically the R, this is R in 2, this is R out 1. So this is the voltage division of this particular source between those two resistors. So therefore this is equal to R in 2 over R in 2 plus R out 1, that's that. And similarly you can write all these other terms. Vn is the input to the nth stage, which should be the output of the previous stage, that will be R in n minus 1 divided by R in n minus 1 plus R in n divided by R out n minus 1. Okay, so Vn is equal to R in n over R in n plus R n minus 1, and V out is the output of the last stage. It is equal to RL divided by RL plus R out. So let's combine all these voltages together to get, actually this should be Vn over Vn minus 1. It should be V out over Vn. Okay, so there was a mistake. Right, so let's combine this to get the overall voltage gain. AV is equal to, you have all these AV terms, AV1, AVn minus 1 up to AVn, so you all have all those, so therefore you will have all those terms, AV1, AV2 up to AVn times, then you have these loading effects. These are called loading effects. This is a loading effect. This is a loading effect. This is a loading effect. Okay. So these loading effect terms comes in. The first one is the loading of the source, R in 1 over R in 1 plus Rs times R in 2 over R in 2 plus R in R out 1 times R in n minus R in n over R in n plus R out n minus 1 times the last term, the loading of the actual load, RL over RL plus R out n. Okay, so this is the loading. These are loading effect, right? So therefore you can observe that the overall gain, this depends on RS, RL and all input and output impedances of the stages. Okay, so that needs to be remembered. However, when you have ideal stages like input impedance is infinity and output impedance is 0, then of course this loading effect will go away, and you will have the total overall gain will be equal to the gain of each individual stage multiplied together. Now this loading effect, you can actually, it doesn't have to be ideal, as long as they are close to ideal, we will have very close to the total overall gain. Okay, so the load on the first stage is the input resistance of the source. The load on the first stage is the input resistance of the second stage, and the source resistance of the ith stage will be the output resistance of the I minus 1th stage. And similarly, the load on the ith stage will be the input impedance of the I plus 1th stage. And if it is the last stage, the load will be the actual load that is connected. If it is the first stage, the input resistance of the source, the source resistance will be the source resistance of the actual source. Okay, right. So with this, we can have different types of amplifier configurations for each different stage, and therefore you can have different input impedances and output impedances for different stages. What matters is that if you have a very high input impedance Ri1 as the first stage, like in the common collector amplifier, and a very low output impedance stage as the last or the nth stage, like the common collector amplifier again, then what you will have is you can acquire the high gain through multiple stages in between. They can be common emitter stages. So this way you can achieve very high voltage gain, very high input impedance and very low output impedance amplifiers. Alright, so we have these features. Okay, so this is why we need cascading or multi-stage cascading in amplifiers. Okay, next we are going to talk about how to connect different stages. This is called coupling. Okay, stage 1 has to be connected to the stage 2. How are you going to connect them? Are you directly going to connect them, or are you going to connect them in a different way? Right, in the example that we looked at, we only had one stage, but the way we connected the input to the source source to the amplifier was through a capacitor. Why was that? To avoid any upsetting of biasing, right? So we need to keep in mind that all these stages needs to be properly biased. Different stages may need different biasing uh, cue points, right? So therefore, when you connect each of these stages, we have to keep in mind not to upset the biasing, right? The biasing has to be kept where it is. So therefore, sometimes we may be able to connect them directly, sometimes we may have to connect them through capacitors, right? So looking at this, we are going to talk next about several techniques that we have for coupling. Okay, so these are called types of coupling. So how do we what are the different ways of coupling? So what are the considerations in coupling? One is we have to make sure that the loss of voltage between stages is minimum loss of voltage between stages. Number two is that biasing should not be affected. Those are the two important things, right? So what are the methods? We are going to talk about four methods. The first one we talked already, we looked at briefly, which is called the capacitor coupling or the RC coupling, okay, or AC coupling, RC coupling, or you also call it AC coupling. Number two is direct coupling, that is without using any capacitors. Okay, the third method we call impedance coupling, and the fourth transformer coupling. These last two methods, though we include for the completeness of the note, these are used mainly for high frequency applications, and we are not going to talk too much about these two, but we will introduce what they are. But the first two are important, the RC coupling and direct coupling. Okay, so let's look at each of these. The first one, the RC OAC coupling. So here the stages are coupled via coupling capacitors. This is what we did in the previous example, where you have the source connected to the amplifier using a input coupling capacitor, and output was taken out through a coupling capacitor, output coupling capacitor. So this is basically what we are going to use for the stages in between also. So let's look at an example circuit. So let's have the first stage, maybe a common emitter circuit, just like what we saw. Maybe there's emitter resistor also, which is bypass capacitor. So this is a first stage is a common emitter stage. It is connected to the source through the signal input. It is connected through a coupling capacitor CC. Output taken from this again coupled through this, right? This is VCC. Now remember, since we are going to couple it through a capacitor, we need to have a second biasing scheme to bias the second stage. So let's bias it again. Okay, so we can use the same voltage source. Let's assume this one is a common collector one. Okay, so this is a common collector stage where my output is taken from the emitter to the load. This may be my RL load. This is my output coupling capacitor. This may be input output capacitor. These are coupling capacitors between stages. Okay, so this is basically, this is one of the stages. This is stage 1, this is stage 2, stage 1, stage 2, and they are coupled through this. These are the coupling capacitors. So this is basically what we do in RC coupling. Okay, so what are some of the features of this technique? So because we couple through the capacitors, we don't have to worry about upsetting the bias of each of the stages. So biasing can be done independently without worrying about what happens the bias voltage when you connect the next stage, the previous stage, right? So those capacitors act as open circuit for DC. But AC analysis is done when you are doing the AC analysis to find the parameters, input output voltage, input output impedances, and the voltage and current gains. You simply replace the BJT with the small signal model, short circuit the capacitors, you obtain the final circuit and analyze it. So it is simple analysis. So that's about the RC coupling. So it is the simplest to analyze because we don't have to worry about each different stage. You can analyze separately and connect if needed. But the next one that we're going to talk about is the direct coupling. Number 2 is direct coupling. As the name suggests, the coupling between stages and between the load and the circuit and the source and the circuit is done directly without connecting any capacitors. No capacitors involved. It's just simply connected. So therefore this is a little bit more complicated because you need to keep in mind not to upset the bias when you are connecting the source to the input stage, or the first stage to the second stage, or the and likewise next stages. You need to ensure that the biasing does not get affected. So when you calculate the Q point, you need to do the analysis to find the Q points of each stage at the same time. So when you decide the Q point of the first stage, you need to at the same time determine the Q point of the second, third and other stages, because you don't have individual biasing for each different stages. The first stage has a separate bias circuit. This will have an output DC value that will serve as the bias point for the second stage, and likewise. Okay, so this is a little bit more complicated than the AC coupling, but it will have less number of components. It will have less number of capacitors. It doesn't have any capacitors, so it's less number of components, and also it's more optimized, but uh, it's a little bit harder to do the analysis. You will have a practical or the design task to design a two-stage direct coupled amplifier. So for the design, this is what you have. Okay, so it will give you a good exercise uh, to design multiple stages, the biasing of multiple stages simultaneously. So let's draw another example circuit. So you have the biasing of the first stage, you have common emitter amplifier. So this is something like this. Directly connect the signal source. This Vs should not have any DC component, otherwise it will affect the biasing. And then you'll have the second stage directly coupled to the first stage, and load is also connected directly to the circuit. Okay, so this is an example of direct coupling. Okay, this is my RL, this is RE, RC1, RE2. This is the biasing R1 and R2. Okay, so this basically is an example of direct coupling. What are some features of this kind of one? The DC analysis is complicated, and the AC analysis, just like before, is done by replacing the BJTs with its small signal not relevant one. It can be the common, it could be the common emitter parameters, or whatever the parameters that you may have. And remember that because there are multiple transistors, you may have multiple models. The parameters for multiple different transistors may not be the same. For one, you may have one set of parameters and another set for the other transistors. So therefore you have to have parameters for each of these transistors. Okay, that's the second one. Then we'll briefly look at the other two as well. So the third one we are going to talk about is impedance coupling, and as I mentioned before, these are used for high frequency applications. At high frequencies, inductors appear as open circuit, right? Very high frequencies, inductors appear as open circuit, and at low frequencies they appear as short circuits, the opposite of the capacitors. Capacitors for low frequencies or DC, they appear open circuit, high frequencies short circuit. This is the opposite of that. So what we are going to do is at operating frequencies, if you make the impedances behave as high resistors or high impedances, then we can actually use this in our circuit. The reason for this is most of the circuits we had RC, okay, and the resistor in the collector circuit, across which we had a large power dissipation, I squared R, IC squared RC. This energy, this power was not useful because our load was separately connected, the RL. So the RC, the power across this was a waste. There is no usefulness for this voltage, this power across RC, unless RC itself is the load. So therefore, to achieve this voltage drop in the load line, we are going to use, instead of RC, because it is at high frequency, we are going to use an inductor so that it behaves like a high impedance, okay, without the loss, without the I squared R loss, okay. But there are few problems with this. We'll talk about those when we talk about the features, okay. So we'll write some notes. So let's look at an example circuit. Let's assume we have biasing that, and the circuit is connected to the source through a resistor, the capacitor, like before. And you have the first stage. Maybe this is a common emitter amplifier configuration with an emitter resistor. Now instead of RC, I'm going to put a inductor, right? So this is an inductor. Inductor is connected to VCC. So this is my first stage. The second stage, I'm going to have another biasing for the second stage, just like in the RC coupling case. And let's say this one is again another common emitter circuit, just like before, okay. And again I'm gonna have another coupled inductor. So this is my setup. Now I mean, to couple this to the next one, we couple through another capacitor. So in this case, the coupling actually happens as an RC, but instead of the resistor RC, now you have an inductor, okay. Output I can obtain from here through a capacitor, just like the inductor. This is my load. This is this is one of these. So the features of this circuit, this is used for RF applications, RF amplifiers above 20 kilohertz. Okay, we are not going to design these in this course, but these are expensive because RF chokes, the inductors, are relatively expensive. RF chokes of the inductors are relatively expensive, but no power loss across RC. This is what we try to achieve there, okay. So in this case, what are my stages? This is one stage, this is another stage, okay. These are stage 1 and stage 2. The previous case, direct coupled one, so this is one stage, and this is the second stage, right. The last one that we are going to talk about is called the transformer coupling. The fourth method is transformer coupling. So here again, we are going to eliminate the capacitor by coupling the stages through a secondary winding of a transistor, because we already have an inductor which we can use the primary winding of a transistor to replace the inductor, like that. So we replace the RC with a primary winding of the transformer and take out the signal for the next stage using the secondary side. So again, you see the DC is blocked, so the biasing will not get upset, and also, as before, no power loss across the RC. So let's have a look at an example. So you have the source which we connect through, again, a transformer, primary side. The secondary side is like that. So we need to connect to my biased circuit. So this is my biasing circuit. This is my first stage. Now this side you have primary winding of the second transformer here, okay. So this is like that. Now we need to connect this to my circuit. So this is how we are going to connect it. This is how you are going to connect it. Similarly, the second stage is going to be there. You have to have another biasing scheme, another transistor, that you may have this, and again you will have a primary of another transistor, and the output is taken from there, the load directly connected to that transformer. You don't have to have a DC bias for that. So like that. So you can see the load is isolated. There is no connection. You can we can even eliminate this ground if you want an isolated circuit. Okay, so you can just have it like that, so that no currents can flow between the RL side and the other. So you need to connect this also through, so you have that kind of coupling. So this is the transformer coupling. Okay, here the first stage is, this is my first stage, this is my second stage. So what are some features? So you have, at low frequencies the required size and cost of transformers increase, because lower the size the bigger the transformer. At high frequencies you can have small transformers, but at low frequencies, so therefore we normally don't use this at low frequencies. We use it for frequencies higher than megahertz, right? Several megahertz. So that means used only at high frequency applications. And also we can have isolation, and the load can be isolated. So those are the properties of this circuit. Okay, so these are the features of uh, the transformer coupling, and with that the coupling types is concluded. So we have four different types of coupling between multi-stage amplifiers at different stages. The next what we are going to do is basically uh, multi-stage amplifier design considerations. Okay, typically for voltage amplifiers we like to have high input impedance, low output impedance, and high voltage gain. To achieve high input impedance, as we mentioned before, we need to use a common collect amplifier configuration as the first stage, so that it has an input impedance of in the range of 100 kilo ohms. To achieve low output impedance also, we can use a common collect configuration as the final stage, because they have output impedance in the range of 100 ohms. So this is good for a output stage. But to achieve the high gain, as again mentioned before, we need to have common emitter amplifiers, so that you can have higher voltage gain. The second or the third, or if you have multiple stages, you can have several common emitter amplifier stages to achieve the high voltage gain. Now you need to remember that you cannot arbitrarily increase the gain. Gain cannot be really high. Say for example, if you want to increase the gain to let's say 100,000 or 1 million, that is not possible without adversely affecting the performance, because inherently where there are even when there is nothing else, whenever there is a resistor, there's a what is called the thermal resistance noise. So therefore noise is there. So this noise, which is typically in the range of nanovolts to several microvolts, when you have multiple stages of amplification, these very tiny voltages get amplified. So therefore at the end, this noise becomes a problem. So therefore typically we do not arbitrarily increase the gain by having multiple stages. Okay, so let's take these notes down. Okay, so here these are the notes. So let's have a look at an example. Okay, so here's an example circuit. So you have stage 1, stage 2, stage 3, and stage 4. So there are 4 stages. Stage 1 is what type? So you see that I have used an PNP transistor. So PNP type, the output is taken from the emitter. So this is the emitter. So therefore this is a common collector. First stage. Second one is the typical common emitter. Third one is a common emitter. And the last one is also, you see, the same as the first one, is a common collector. Okay, so you have common collector, common emitter. These are PNP, NPN, PNP. So I have used PNP as well as NPNs. So far we have never seen PNPs in our circuits. And you might ask, how do you analyze a circuit when you have a PNP transistor? The answer to that is, you do not differentiate between NP and PNP. You just assume it's the same. So wherever you have PNP, you just don't assume it any different when it comes to the small signal analysis. In the small signal analysis, you replace it exactly with the small signal analysis circuit, small signal model, H parameter model, as if you had a NPN transistor. The only difference is that all the voltages and currents will be negative. In other words, they are the opposite. That is the only difference that you will see. So therefore, you do not make any difference. You do not differentiate between PNP and NPN. Just put the same small signal model. Okay, so you have this. So you see that I have emitter resistors in the RE1, RE2, RE3. These are there to reduce the DC gain. You remember that the gain is roughly equal to the resistance in the collector divided by the resistance in the emitter. So you will see that the middle stages you have emitter resistors. So therefore RC2 divided by RC, RC2 divided by RC2 divided by RE2 will roughly be the DC gain, whereas now I have the capacitor bypass for each of these stages. So the AC gain will be high, though the DC gain is low. So second stage and the third stage will have that feature, right? So RE1 and RE4 are the main resistors through which you take the voltage. Okay, and there is only one biasing circuit, R1 and R2. So this is a direct biasing scheme. As you can see, you'll have to do the biasing for all four stages by setting R1 and R2. So this is a little bit difficult, more complicated than AC coupled circuit. But this, because of this particular configurations, input impedance of this is high input impedance and low output impedance because of the common collector. These will have high AV. Okay, so the overall gain, so the AV here is 1, so therefore the total gain would be AV2 times AV3 roughly, if you neglect the loading effect. But if you take into consideration the loading, it will be a little bit less, but still you can make AV2 and AV3 large and thereby having a large voltage gain with high input impedance and low output impedance. Alright, so why do we use these PNP transistors in this circuit in addition to the PNP, NPN transistors? Now, this is an important design feature. By using NPN and PNP transistors both in the same circuit, we can reduce the effects of temperature. We basically compensate for temperature effects. So this is the main reason why in practical designs you have NPN and PNP transistors together. Okay, so let me write that down. NPN and PNP transistors both in the same circuit compensates effects of temperature. Therefore, it is good to have both in these circuits. Okay, so this is where we are going to stop today, and that concludes our section on multi-stage amplifiers. If you have any questions, please do not hesitate to contact me through fields or by email. I will try to help you as much as possible. Make sure that you understand this before you go to the exams. Thank you and good luck.